Welcome to this tutorial on flanged beams in reinforced concrete according to the Eurocodes. In the previous tutorial, we went over the theory quite quickly, so if you need a little recap, go back there. If not, we're going to go over the flowchart and dive straight in. Before we start example 2 on flanged beams, I want you to remember that the full theory and all the derivations for flanged beams are covered in the lectures, and they're summarised again in tutorial 1. All the theory, including the different compression cases, the limiting moments, and the neutral axis check, is brought together in this flowchart. It provides the full decision process, starting with the effective flange, width, and the design moment. And then we check if the flange alone can carry the compression block, like we found in the previous example. And finally, we can determine whether the section can resist the moment without compression reinforcement. So let's get into our second example. Here we've got a flanged beam, or a T-beam. It's already giving us the effective width of the flange at 580 millimeters. The height of the flange, or the height of the slab, is 100 millimeters. The height of the whole T-section is 420 millimeters. The effective depth is 380, and the width of the web is 250 millimeters. We're already given an ultimate moment of 340 kilonewton meters, so we don't have to calculate the moment or the effective width in this case. And we know the strength of the concrete is 25 megapascals and the strength of steel 500 megapascals. We're also given the depth of the neutral axis at the ultimate limit state, xu, as 0.448 d. We need to find, once again, the area of reinforcement. To do that, we'll first check if the stress block is in the flange, check if compression steel is required, and then we'll be able to determine how to find the required reinforcement. So just as before, I start off by listing all of my input. I've taken all the geometrical knowledge that's available on the sketch and put that into my input. I've also added the ultimate moment of 340 kilonewton meters, the depth to the neutral axis, and the strength of both concrete and steel. So the first thing I want to do is check if the stress block is inside the flange. If it is, we can simply design this as a rectangular beam of B effective on D. If it isn't, then we'll have to approach it a bit differently. So the first thing we do is we calculate what is the moment that the flange can carry. To do that, we take eta, which is 1, times FCD, which is the strength of concrete divided by the safety factor of 1.5, times the effective B, which we already know is 580, times the height of the flange, or the height of the slab, which is 100, and all that times 380, which is the effective depth, minus the height of the flange divided by 2. We then multiply that by 10 to the minus 6, and that is just to organise my units, because FCD is in megapascals, which is units to millimetres square, and the rest of the units here are millimetres, and I want to view this moment in kilonewton meters, and that's just to make it easier to compare to the moment that I already have. If I do this calculation, I find out that the moment in the flange is 319 kilonewton meters. Now we have a moment acting on this beam of 340 kilonewton meters. We need to check if that moment that is acting on the beam is smaller than the moment that the flange can carry. Now, unfortunately, in this case, it isn't, and that means that the stress block extends into the web. So we've just found that the stress block extends into the web. Now we want to check if compression steel is required. Now this is unlikely, but we still need to check. So this is the equation. What we're looking for here is M max. This is the maximum moment that the section can carry without the need for compression steel. And the way this equation is written is M max divided by the effective width of the flange, B effective, times D squared, the effective depth, times FCD. And that has to equal this whole equation here. Let's see what that entails. So we start off by solving the right-hand side of the equation. So you have eta, which is 1, and then we have in the first brackets 1 minus BW, the width of the web, which is 250, divided by the width of the flange, which is 580. That gets multiplied by HF over D, which is 100 over 380. And then we multiply that by 1 minus HF, the height of the flange, or the height of the slab, divided by 2 times the effective depth. Onto that, we add eta, which is 1, times lambda, which is 0.8, and all of these things are derived previously in the lectures, if you're wondering where they're from. That gets times by BW divided by B effective, so once again 250 divided by 580, and then multiplied by xu over d. Now xu was given to us as 0.448d, so the d and the d cancel each other out, and then we're left with 1 minus 0.5 times lambda, so once again 0.8, times xu over d, so once again 0.448. And that gives us 0.257. Now that we have the right-hand side, we can multiply it by the effective times d squared times FCD to isolate the maximum moment. And if we do that, we need to multiply the number we got on the right by 580 times 380 squared times 25 over 1.5. And just to organize our units so that we get kilonewton meters times 10 to the minus 6. And we get a maximum moment of 358.5. What we need to check now is the moment that we have to design our beam for, that 340, is it smaller than the maximum moment that the section can carry in compression? If it is, that's fine. We don't need any compression reinforcement. If it wasn't, we would have to design for compression reinforcement or to change the section. So now that we know two main things about our design, one, that the stress block goes into the web, two, we don't need compression reinforcement, we can now find the required reinforcement. To do that, the first thing we need to do is determine the depth of the neutral axis. And to do that, we need to look at this equation. And what we can see here is that once again, on the left-hand side, we have our moment divided by the effective B times d squared times FCD. And once again, on the right-hand side, we have two parts. And that gives us all the information we need to determine x over d. But it is a little bit tricky. So let's go through this step by step. So on the left-hand side, we've got our moment, our design moment of 340, divided by the effective B of 580 times d squared, so 380 squared, and times FCD, so the strength of concrete divided by the safety factor. Then in the first part of the right-hand side, we have eta, and then we have 1 minus BW over BF times HF over D, and all that times 1 minus HF over 2D. That's the first part. The second part, just like before, we have 0.8 times 250 over 580, so BW over BF, times X over D, and all that multiplied by 1 minus 0.5 lambda times X over D. If we open the brackets and reorganize it, we'll see that on the left-hand side we get 0.243, and on the right-hand side we get 0.13 plus 0.345 x over d minus 1.38 x over d squared. So bringing everything to one side of the equation and dividing by 0.138 will give us x over d squared minus 2.5 x over d plus 0.823. And that's the equation that we need to solve. So as you can see, it is a quadratic equation, right? X over d squared minus 2.5 x over d plus 0.823. So a blast from the past, I'm sure you all remember this, but solving a quadratic equation and finding the roots is given by x equals minus b plus minus a square root of b squared minus 4ac over 2a. And if we implement it in our equation, we find that x over d is 2.5 minus the square root of 2.5 squared minus 4 times 1 times 0.823 divided by 2. And that gives us 0.39. The other root, if you solve it, just is irrelevant for this solution. Now, xu over d, the limit was 0.448. So we need to first check that the x over d that we got is smaller than that limit, and it is. So that's great news. And that means that x equals 0.39 times d, which works out as 148 millimeters. So that is x, the depth to the neutral axis, 148 millimeters. And now we need to calculate the two parts of the compressive forces. C1, which is the bits of the flange, which I've coloured here in blue just to clarify, is eta times FCD times B effective minus BW, which essentially gives us the length of those two blue bits together, times HF, which gives us the height of those two blue rectangles. And if we multiply those, so 1 times FCD, which is the strength of concrete divided by the safety factor of 1.5, times B effective minus BW, so 580 minus 250, times the height of the flange 100, and then times 10 to the minus 3, just to organize my units from newtons to kilonewtons, I get 550 kilonewtons. Now that is the compression force that the flanged bits of the section provide. I also need to find the orange bit, which is the bit that the web provides. So here you can see that I take the BW times lambda x, which is that height of the orange bit or the bit of the web that's in compression. So once again, I have eta, which is 1, times FCD, which is 25, divided by the safety factor of 1.5 for concrete, times BW, 250, times lambda x, which is 0.8, times x that we just found. And all of that times 10 to the minus 3 gives us 494.25 kilonewtons. So in total, C1 and C2 are the two compressive forces that the concrete provides. Now, from equilibrium, we know that the force T, the tension force, which is provided by the tensile reinforcement, has to equal to the compressive forces. Okay, that is the premise of all of our reinforced concrete design. T equals 0.87 times Fyk times the area of steel, and that has to equal to C1 plus C2. Now, since we know the strength of steel as 500, we've got 0.87 times 500 times the area of steel, and that needs to equal to C1 plus C2. Just organizing my units here because the 500 is in megapascals. And from here, I can isolate AS and find that it is 2,400 millimeters square. And that is the area of steel that I need to provide to have a balanced section. And that is how you solve a flanged beam when the stress block continues into the web. And that's how we solve a flanged beam when the stress block continues into the web. I hope that was helpful, and I hope I see you again for some more reinforced concrete design.